Hello everyone. So my name is Weiwei Tang, and I'm from Tianjin University, and my major actually is chemical engineering. I know maybe a little bit uh, far away from your majors, but my study I'm very interested in the try to use the natural resource like Chinese herbals to find some more inhibitor monomer for the treatment of kidney stones. Okay, so today my presentation topic is developing Chinese urban polyphenol inhibitors for prevention of pathological kidney stones. Okay. So in this presentation, I would like to first give a brief background about kidney stone, and then I would like to talk about the principle and the strategy to prevent kidney stone by using crystal growth inhibition knowledge. Lastly, I would like to present our recent work on developing Chinese urban polyphenol inhibitors for prevention of two most common types of kidney stones. One is calcium oxalate stone, and another is urea stone. So what is kidney stone? So kidney stone is a common urinary disease due to the deposition of inorganic or organic mineral in kidney. So it has global incidence about 5 to 15% and affecting hundreds of millions of people. So the prevalence in China is about 6%. That is equal to like one patient every 70 people. So the great challenge for the treatment of kidney stone so are the high recurrence rate after surgery is up to 52% within 5 years, and no therapeutic change in 30 years. So kidney stone are crystalline aggregates. So according to their components, so kidney stone are classified into calcium oxalate stone, which occupies around 70 to 80%, and the urea stone about 10 to 15%, and as well as strawberry, brushite, and L-cysteine stone. So the first question we might ask how the kidney stone are formed. So let's see this video first.
Such as calcium oxalate, that have been filtered into the urine by the kidney, spontaneously joined together to form a solid crystallinus. This is called nucleation. There are two kinds of nucleation. In homogeneous nucleation, crystals form around the nucleus with the same composition. Crystals of a different composition can put off renal papilla. They undergo the next major phase, put off. Crystals that have already formed then begin to stick together, forming large aggregates. As we can see, crystals can aggregate very quickly. New stones are retained in the kidney, where they can continue to grow for an unspecified length of time, until for reasons that are not well understood, they are displaced and travel through the kidney into the ureter. If a stone continues to grow until it reaches a critical size, which can be as small as 4 to 5 millimeters in diameter, it may be too large to pass easily through the ureter. The edges of the stone may become wedged inside the ureter at the ureteropelvic junction, where the ureter crosses over the iliac artery, or the ureterovesical junction. The result, pain and obstruction, until the stone slowly passes into the bladder and eventually passes out of the body in the urine stream.
So from this video, we know that kidney stone formation typically includes the following steps. The first step is the generation or supersaturation in the urine, and then the nucleation and crystal growth, and subsequently crystal aggregation and fermentation in kidney to form kidney stone. So therefore, crystallization is a key step for the kidney stone formation. So currently, there are two types of crystallization mechanism, namely the classical and the non-classical mechanisms. So the classical mechanism solves the atoms or molecules are transformed into crystalline by one step and further grows into a microscopic crystal by multifaceted mediated crystal growth. Whereas the non-classical mechanism saw the atoms or molecules first form the cluster or amorphous precursors and then transform into crystalline nuclei. The surface growth may proceed by the attachment of nanoparticles. So according to the classical crystal growth mechanism, the step propagates on the crystal surface to form new layers, and there are three types of growth sites. One is king size, another step size, and terror size. So slopes can be incorporated into the king size by either direct incorporation or surface diffusion pathways to realize the step propagation. So in the presence of growth modifiers, they may absorb one of these size and inhibit the stable propagation and thus inhibit the surface growth. So this is reflected by the formation of this rough and corrugated steps. So when isotropic surface growth rate was affected by the growth modifier, so the morphology will be changed. As shown here, maybe changing from like hexagonal shape to the pattern-like morphology. So this molecular recognition process can be achieved by modifying molecular structure, function groups, stereochemistry, or spatial sequence of growth modifiers. So common growth modifiers can be ions, molecules, or micromolecules. So the morphology of calcium oxide monohydrate usually display hexagonal shape with the exposed surface mainly 100 and 020. So the 10 crystal surface grows by the triangular heel knock spiral dislocation, whereas the side 010 surface grow by rhombic heel knock. So growth modifiers or inhibitors with anionic moieties such as glutamic acid, aspartic acid, can bind into this crystal surface via the carboxylated calcium carboxylated bridge structure. So which will change the crystal morphology and reduce the growth rates. So this molecular recognition principle has been utilized to rational design inhibitors such as proteins, peptides, and organics. So our strategy is to develop new inhibitors from Chinese urban medicine for the prevention and the treatment of kidney stones. So to achieve this goal, we firstly establish a high throughput screen method of inhibitors from Chinese urban medicine. So the screen method typically includes the extraction, separation, the inhibition performance evaluation, and the HPLC identification of small organics. So by using this method, we successfully identify 13 inhibitor molecules that are polyphenols, amino acids, and AD promoters from Chinese urbans, from 20 kinds of Chinese urbans. We further evaluate the inhibition efficacy of these inhibitors by using the single crystal growth experiments and establish the specific sites of interaction between inhibitors and the crystal surface. Through in vitro cell experiments, we found that these inhibitors can significantly inhibit the crystal nucleation and adhesion to the renal epithelial cells. So interestingly, we observe a concentration-dependent inhibition performance of polyphenol inhibitors. So while talic acid is a potent inhibitor, it displays growth promotion and low concentrations, whereas we observe the formation of crystal wicks on the side 010 surface. Similarly, enantiotic acid can also display the growth promotion and low concentrations. So we are curious about why the inhibitors can promote crystal growth. To elucidate the underlying mechanism, we use the in situ atomic force microscopy to study the surface growth dynamics. So here we found that when the inhibitor was introduced, the crystal growth mechanism was changed from the spiral growth to the two nucleation and the growth mechanism. So as here's a video, as you can see here. So they show the spiral growth on this 010 surface. And once when the inhibitor was introduced, the surface become the 2D nucleation and growth mechanism, where you can see the formation of these stable bunches. So this stable bunch will be further evolved into the microscopic crystal wicks. So there are diverse modes of inhibition actions. So stepping and the king blocking are the two most common mechanisms. So as you can hear, so the addition of EA inhibitor will significantly reduce the step velocity on the 100 surface, and also display the rough and the corrugated steps. So which suggests a stepping inhibition mechanism. Whereas on the 010 surface, so we still see the step velocity decrease. This is due to the addition of EA inhibitor, but they are not, they will never over to a constant value. This indicates a king block inhibition mechanism. Sometimes inhibition mechanism can be more complicated. For example, shown here is a dual mechanism of stepping and king block. So to compare with GAA, which is a stepping, so the step velocity in the presence of PGA inhibitor show much steeply decrease. So this is due to the effect of inhibitor molecules absorbed on the terra and king sites simultaneously, which display a dual mechanism of stepping and king block. Then we want to enhance or improve our inhibition performance, try to use inhibitor combinations. So we selected the 4 inhibitor combinations, which covers the stepping and the king block inhibitor with a stepping inhibitor, or stepping and king block inhibitor with a king block inhibitor, or stepping and king block inhibitor with a stepping and king block inhibitor. So surprisingly, we observe a strong synergistic cooperative between inhibitors. So for example, the combination of citric acid with gallic acid display a 4-fold growth inhibition enhancement compared with CA annoying. Oops. So we further to validate the synergy between inhibitors by using in situ atomic force microscopy. So the inhibitor combination displays the rapid decrease of step velocity compared with CA annoying in all 3 growth directions, which suggests the strong synergistic inhibition. Then we further investigate the inhibition efficacy of these binary inhibitors on cell rotation and kidney stone formation in mouse. So here, as you can see, so the combination of CA and polyphenol inhibitors can significantly reduce the calcium, the adhesion of calcium crystal to the renal epithelial cells, and that shows this significant synergistic characteristics on the suppression of calcium crystal adhesion. Besides, we also observe a synergistic reduction on calcium oxalate deposition in kidney and the renal injury in mouse. So the urine stone is relatively rare in human, but the main kidney stone for dolphins. So why we care dolphin kidney stones? So bottlenose dolphin can be of great importance for military use and are endangered species with only 3,000 in population of the world. And the kidney stone are one of the main causes for high morbidity and mortality of dolphins. So the structure of urate is relatively simple, and the crystal structure of urate monohydrate has been fully determined since 1974. However, the structure determination of ammonium urate is difficult and challenging. So this is due to the numerous crystal defects are formed during crystal growth. So we found high pH effects of crystal growth and successfully determine the ammonium urate crystal micronite by using 3-dimensional in natural diffraction techniques. So under neutral pH conditions, we found that the ammonium urate crystal tend to grow into this dumbbell-like shape or bending crystal with a large number of crystal defects. So by using microfluidics growth device, we measure crystal growth rate as function of urate concentration at both pH 11 and pH 7. So where we observe unique self-inhibited growth cessation in supercellular concentrations. So this is a very unusual and phenomenon. We further investigated the surface growth dynamics at the crystal liquid interface by FM. At pH 11, we see the surface growth proceeds by neonucleation and spreading mechanisms, and the surface step velocity measurements also reveals a typically nonlinear increase as function of urate concentrations. Whereas in contrast, so under neutral conditions, While although the surface growth still proceeds by neonucleation and spreading mechanism, but the steps display much rough and corrugated features. Besides, the stability measurements also confirms the presence of self-inhibited growth cessation region in high surface area concentrations. Then we would like to know what's happening. So by using DMT calculation and IR spectroscopy measurements, so we confirm the urea tautomerism in solution, and this minor tautomer presence leads to the growth cessation of crystal growth. Then we revealed as new self-inhibited crystallization mechanism. We found that the urea tautomer is a unique and potent inhibitor that functions as a dual mechanism of stepping and king block to suppress crystal growth of amino urate. Then we further investigated the university of this self-inhibited crystallization phenomenon. We've observed a similar self-inhibited growth in another two systems where we observed the growth cessation in supersaturation concentrations. So to summarize, we found diverse mechanism of growth inhibition by inhibitors. So the concentration threshold of an inhibitor may alter crystal growth inhibition to growth promotion regime. We demonstrated that the inhibition performs on cell adhesion, stone formation, and kidney injury can be improved using synergistic cooperativity between inhibitors. We discovered that the keto-eno tautomer is a new class of potent inhibitor that produces self-inhibited crystallization phenomena. Finally, we extended the tautomer-induced self-inhibited crystallization to biological and pharmaceutical molecular systems. Finally, I would like to acknowledge funding support from NSFC and all the group members and the students, as well as my collaborators. So thank you for your attention. I would like to take any questions if you may have. That's it, Roy. Thank you.